The rate law expression, or often called the rate law, is used to describe how the rate of a reaction depends on concentrations. This rate law is experimentally deduced for each reaction from a study of how its rate varies with concentration. The rate law expression for a reaction in which A and B are reactants has the general form rate is equal to K times the concentration of A raised to X times the concentration of B raised to Y. The constant K is called the specific rate constant, or simply the rate constant, for the reaction at a particular temperature. The values of the exponents x and y and of the rate constant k bear no necessary relationship to the coefficients in the balanced chemical equation for the overall reaction and must be determined experimentally.
The value of x and y are usually small integers, or zero, but are occasionally fractional, or even negative. A power of 1 means that the rate is directly proportional to the concentration of that reactant. A power of 2 means that the rate is directly proportional to the square of that concentration. A power of 0 means that the rate does not depend on the concentration of that reactant, so long as some of the reactant is present. The value of x is said to be the order of reaction with respect to A, and y is the order of the reaction with respect to B. The overall order of the reaction is the sum of the reactant orders, x plus y. Note, the orders or exponents in the rate law expression may or may not match the coefficients in the balanced equation.
Here are some examples of observed rate laws for some reactions. 3NO decomposes to form N2O and NO2. The rate law expression for this equation is rate is equal to K times the concentration of NO squared. The NO has a second order and the overall order of the reaction is 2. 2NO2 reacts with fluorine to form 2NO2F. The rate law expression for this is rate is equal to K times the concentration of NO2 times the concentration of fluoride. Both the NO2 and the F2 has a first order, and the overall order of reaction is 2. H2O2 reacts with 3I negative and 2H plus to form 2H2O and I3 negative. The expression for this is rate is equal to K times the concentration of H2O2 times the concentration of I negative. The H2O2 has a first order, the I negative has a first order, and the H plus has a zero order. The equation has a second order overall. It is important to remember the following points about the specific rate constant K. Experimental data must first be used to determine the reaction orders and then the value of K for the reaction at appropriate conditions. The value we determine is for a specific reaction, represented by a balanced equation. The units of K depend on the overall order of the reaction. The value we determine does not change with concentrations of either reactants or products. The value we determine does not change with time. The value we determine refers to the reaction at a particular temperature and changes if we change the temperature. The value we determine depends on whether a catalyst is present and on the nature of the catalyst. Here is an example regarding the interpretation of the rate law. For a hypothetical reaction, A plus B plus C that will react to form certain products, the rate law is determined to be rate equals K multiplied by the concentration of A raised to the power of 1 times the concentration of B raised to the power of 2. What happens to the reaction rate when we make each of the following concentration changes? Remember that changing concentrations of reactants does not change the value of K. We triple the concentration of A without changing the concentration of B or C. We see that rate is directly proportional to the first power of A. We do not change the concentrations of B or C. Tripling A causes the reaction rate to increase by a factor of 3 raised to the power of 1 or 3, so the reaction rate triples. We triple the concentration of B without changing the concentration of A or C. We see that rate is directly proportional to the second power of B, that is, B squared. We do not change the concentrations of A or C. Tripling B causes the reaction rate to increase by a factor of 3 squared or 9. we tripled the concentration of C without changing the concentration of A or B. The reaction rate is independent of C because it is in zero order, so changing C causes no change in reaction rate.
Method of initial rates is used to deduce the rate law from experimentally measured rate data. Usually, one knows the concentrations of all reactants at the start of the reaction. The initial rate of the reaction can then be measured corresponding to these initial concentrations. For example, refer to the tabulated data to solve the initial rate of the hypothetical reaction at a specific temperature. Because we are describing the same reaction in each experiment, each is governed by the same rate law expression. This expression has the form: the initial concentration of A is the same experiments 1 and 2. For these trials, any change in reaction rate would be due to different initial concentrations of B. Comparing these two experiments, we see that B has changed by a factor of 2. The rate changes by a factor of 2. The exponent y can be deduced from this expression, so y is equal to 1. The reaction is first order in B, thus far we know that the rate law expression is.
To evaluate X, we observe that the concentrations of A are different in experiments 2 and 3. For these two trials, the initial concentration of B is the same, so any change in reaction rate could only be due to different initial concentrations of A. Comparing these two experiments, we see that concentration of A has been increased by a factor of 2. The rate increases by a factor of 4. The exponent X can be deduced from this expression, so X is equal to 2. The reaction is second order in A. We can now write its rate law expression as, now that we know the orders, the specific rate constant, K, can be evaluated by substituting any of the three sets of data into the rate law expression. Using the data from experiment 1 gives, at the temperature at which the measurements were made, the rate law expression for this reaction is